Let's talk about metabolic carts, instruments we use to measure gases that we exhale and inhale. And then ultimately, we are measuring the oxygen in the air that we breathe in. We're measuring the oxygen of the air we exhale, as well as carbon dioxide that we inhale and exhale. And that's what a metabolic cart is designed to do. And I'll talk about a few different variations of metabolic carts. But this is the physiology behind what a metabolic cart is trying to do. We have chemical potential energy in our body, carbohydrates, fats, and proteins. And we take that potential energy into chemical bonds and we transform that energy to mechanical energy, or force that's going to cause motion. The way we transform this potential energy to mechanical energy is through our aerobic and anaerobic pathways. You should know your pathways. You've had classes on the aerobic pathway, the anaerobic pathways, and what have you. And what we're ultimately trying to do in training someone for an endurance event is we're trying to manipulate frequency of exercise, intensity of exercise, how long we exercise, what type of exercise we do, ultimately to improve the aerobic system and or the anaerobic system. And we do that by monitoring different things, heart rate, power, RPE, what have you. And there's a lot that goes into this transformation in terms of thermoregulation, that the transformation of potential chemical energy to mechanical energy is not a perfect transformation. If we have 100 units of potential energy here, we may only get about 30 units of energy over here. So where's that other 70 units go? It goes off typically as heat. And so we're generating heat as we are making this transformation happen. Okay, so what do? Well, aerobic system obviously has to do with oxygen. And so we have these instruments available to measure the air that a person breathes in and exhales. Remember, air is oxygen, carbon dioxide, and other stuff. Okay, and we're using these instruments to be able to take to measure the air that's coming in, how much air is coming in, how fast it's coming in, and then what's the content of the air, which is content of the room. And then we breathe that air into the lungs and we extract out the oxygen, ultimately used in the aerobic conversion of transformation of chemical energy to mechanical energy, produce that ATP. And in that process, CO2 is generated by the muscle. That the blood transports that CO2 back to the lungs, and we exhale out air that has a different ratio of oxygen and carbon dioxide in it. And when we can measure what's being exhaled and we know what's being inhaled, we can start understanding how much oxygen was used and how much carbon dioxide was produced. So a sophisticated system runs about $30,000 to $40,000, depending on how many accessories you add on. And this does exactly that. This has a VO2 sensor, it has a VCO2 sensor, and it accurately measures the amount of oxygen and the amount of carbon dioxide in anything that's run through those analyzers. And so if we have a mask on here, you see EKG set up as well. It's common to do both at the same time, but not necessary to have the EKG. Sometimes we just do metabolic processes, and maybe we use one lead, or actually it's a 2-lead system, but we use one unit like a heart rate monitor, chest drill. But there's other systems that have become more portable. With portability changes the information that we get back. This is a system, we have this in our lab, a K5 system. You wear a little bit of a backpack here, and you're still able to get VO2 and VCO2 using this system. Much smaller, more portable, that comes with advantages and disadvantages. Is it's probably just a little less accurate than our in-lab system. Then there's this system here that's even more portable. It is just a face mask unit. And in this system, it only measures, and we have this as well, it only measures rate of oxygen consumption. It does not measure VCO2. VCO2, to get that, you need a whole nother set of instruments within your main instrument to be able to get that. So this throws out the CO2 and is only measuring oxygen consumption. Now, there's two ways to capture the air. Well, more than two ways, but the two general ways is the mask that you saw in the previous pictures, and then what we call a snorkel. And you have a snorkel, and then you've got a nose clip to block any air going in and out of the nose, because we want to measure any air going into the person and out of the person. And so this is a classic way to do it with a snorkel, very secure. The problem is if you wear a snorkel, if you're wearing it for a long time, yeah, it's just sort of, it gets awkward. Sometimes you can get sores in your mouth just because of the rubbing that goes on during exercise. And it's bulky. It's hard to do things like running using this. We do running with it, but it's just a bulky system. This is a much cleaner system. The downside of this, if you have any facial hair, you can have leakage in the mask, and even the way your face is shaped, if it doesn't seal well with the mask, you're going to have errors in the system, because we want to capture all the air coming into the body and all the air exhaling. If we're exhaling and it's leaking out the sides, we're going to have bad data. All right, so the advantage of this is it's a little more comfortable for the user. Disadvantage is you can get some leakages. These are the sensors I talked about. This is an older system. I just found that for the pictures mostly. This has a separate VO2 oxygen sensor and CO2 sensors. And the air comes into the system, and these sensors are, the air is routed through these sensors, and these sensors will kick back the information in terms of how much oxygen is in the air and how much carbon dioxide is in the air, either the air that we're breathing in or the air that we're exhaling. And we want to know those two things. We want to know how much oxygen and carbon dioxide is in the air coming in, and we want to know how much is being exhaled as well. And we want to know how fast the air is moving in and out of the body or in and out of the mask. So why measure both VO2 and VCO2? Well, this really tells us a lot about metabolic processes, the processes used to take chemical energy and transform that over to mechanical energy. VO2 reflects our oxygen consumption, and if I want to talk about rate of oxygen consumption, I should put a dot over this, but we can also talk about VO2 and volume of oxygen. VCO2 reflects carbon dioxide production. Again, I need to put a dot over the V to talk about rate of carbon dioxide product, or rate of carbon dioxide, or we can talk about just volume of carbon dioxide. Together, these two parameters helps us understand metabolic substrate use, and ultimately we use both of these to calculate energy expenditure. So you say on that one system that's only measuring VO2, realize we are not getting the VCO2 part, and that's just a limitation of the instrument. Doesn't mean it's not useful. It just have to use the instrument in a way that reflects what it's doing. All right, so let's look at carbohydrate oxidation equation. So here's our carbohydrate, glucose. We use oxygen, and we combine those two, and through lots of chemical steps, we ultimately produce carbon dioxide, water, and ATP, adenosine triphosphate. What do we do with the carbon dioxide? We exhale it. That's why we're measuring the amount of air being exhaled, is we want to know how much carbon dioxide is being exhaled. And this is the inhalation. This is how much oxygen is going into the system. And we calculate Oh, sorry, I didn't put the equation here. We calculate respiratory equivalent ratio. I don't know why I don't have that in there. As the ratio of carbon dioxide produced and oxygen used. Okay. And if we have 6 units of oxygen used and 6 carbon dioxide produced, we have an RER of 1.0. And that indicates that equal amounts of oxygen is consumed and used and CO2 is being produced. And this would be representative of carbohydrate as the substrate being used to generate the ATP that's ultimately used in cross-bridge formation and generating a force. If we look at fat oxidation, this is an example fat. This is the chemical equation for that fat. We need lots more oxygen, and we produce some carbon dioxide, we produce water, and we actually produce a lot of ATP this way. The respiratory equivalent or exchange ratio is 0.7, which is just the ratio of carbon dioxide produced to the amount of oxygen used. And that comes out to a fraction of 0.7. So when we're looking at an RER of 0.7 or something close to 0.7, we're talking about fats being used as the substrate to do whatever exercise we're doing. We also use the metabolic cart information to calculate the energetic cost of locomotion. This is something I've covered in different lectures in physiology of endurance performance. And we use the Weir equation for that. And this is the equation here. And it calculates energy expenditure in kcals per minute. So calories is a unit of heat, but it equates to the energy used to transform potential energy in the chemical state to mechanical energy in essence. And this is the equation, 3.941 times rate of oxygen consumption. This should be a dot over that, plus 1.106 times VCO2. And so here, to calculate the amount of calories used during exercise, we need both VO2 and VCO2. We need to understand the aerobic and the anaerobic components. So I'm sorry, I didn't get to the anaerobic component in here. I'm sorry I didn't include that in this slide, but we also have anaerobic metabolism of things like carbohydrates as well as creatine phosphate. And when we use carbohydrate anaerobically, we actually generate VCO2 there as well. And so we need to understand rate of carbon dioxide exhaled in order to ultimately calculate energy expenditure that reflects both the aerobic and anaerobic components of generating ATP. In this case, VO2 and VCO2 are just in liters per minute, and we use this to estimate metabolic cost or calories used. All right, so to pull together what a metabolic cart does, it integrates physiology and chemistry and exercise intensity. We're able to determine VO2, VCO2, depending on the instrument, and this gives us some insight into the metabolic pathways and processes that are happening during exercise. RER represents substrate utilization. It's a ratio of VCO2 to VO2. And the Weir equation is used for energetic cost of locomotion. How many calories are used to cover a distance, whether it's swimming, biking, or running. Okay, thanks everyone.